In this question, a water skier lets go of a tow rope upon leaving the end of a jump ramp at a speed of 14 meters a second. At the peak of the skier's jump, his speed is 13 meters a second. Find the height of the skier's jump referenced from the top of the jump ramp. So when trying to deal with this question, there's a few key pieces in this sentence that we need in order to try and answer the said problem. So I'm going to leave it here for a moment. So this is going to be the water. Must be the ocean because it's a little bit wavy. And then we've got some kind of ski jump in the water. And this is obviously a rather large ski jump. Now, we have a skier coming along who's being pulled by a tow rope. And at the point that he reaches the jump, he lets go of the tow rope. Okay, so that's the end of a particular phase. And it's important here that it says that he lets go of the tow rope, because that means that the boat is no longer exerting a force upon the skier. So for the rest of the time, as the skier comes up the jump and then follows an arc back and then back down to the water, this whole time up the ramp, he's going to be moving under his own velocity. So at the top of the ramp when he leaves, we know that he has a velocity of 14 meters a second. And again, they're telling us his velocity, and this is going to be the velocity in the horizontal direction, because this is going to be for the kinetic energy, and kinetic energy only ever concerns itself with horizontal, so left to right motion. At the peak of the jump, so at this point here, they tell us that it's going to be 13 meters a second. So velocity here is 13 meters a second. And again, that's important because we don't know how high this jump is, so we don't know how much further down he goes here. We don't know how far he travels in the entire time. There's a lot of things we don't know in this question, but they're telling us what the velocity is at this point when we come off the ramp, and they tell us what the velocity is at the peak of his jump. And all they want to know is what is this height. And again, that's very important because we don't know what the height of this ramp is. But if instead of using a ground level state, if we just use a reference line, a reference state, if we call this red line here 0, then we can do a mechanical energy problem and find out what is the height that he reaches if he slows down to 13 meters a second. So what they're saying here is he has some amount of energy when he comes off this ramp, and some of that energy is going into throwing him up this way, and some of that energy is being used to throw him this way. So we can figure out how much energy is used up in making him climb whatever this distance h is. Okay, so let's do a quick summary of our knowns. So what are some things that we know that are going to be important for dealing with this question? Now, the things we know for sure is we know that g equals 9.8 meters per second squared, namely because it always equals 9.8 meters per second squared and doesn't change. It's a constant, and we've explored why and how that is before. So unlike in question number 1, we now have actual velocities. The initial velocity is going to be 14 meters a second, and the final velocity is going to be 13 meters a second. And this was given to us in the question, so we know those things. Now, before I go on and do the rest of the knowns, let's go on and talk about that mechanical energy formula. So here, starting with the formula that'll remind us all the aspects we need to keep in mind, we're going to do, well, it's not an equal sign, that's should be a plus, or should be an equal sign, plus sign there. We're going to be doing mechanical energy initial is equal to the mechanical energy final plus some external amount of work. So now in this question, and again, as I explained in the last one, I use this to help formulate my thinking. And one reason why I find this better than others is this right here, and I'll show you how we can get rid of this part of the term right off the bat. As I mentioned, an important part of this question is that the skier let go of the rope here as they entered the ramp. So as they move up this ramp, they're going to, of course, lose some amount of energy due to friction with the ramp, which is why they tell us the speed of the person at the top of the ramp and not at the bottom. So we don't have to worry about the friction. We don't have to worry about the tow rope pulling on the person. So it's just going to be the person free falling or free flying through the air. So there's no external work in this situation. We'll ignore air resistance and all that. So the external work goes to 0. So all we're dealing with in order to solve this problem is mechanical energy of the initial state is equal to mechanical energy of the final state. So now let's take a look at a few things. We know that, and we'll just do a little side note of this for a moment, we know that mechanical energy is equal to the potential energy plus the kinetic energy. Now, before we go to write this down, let's think about this for a moment. Both the initial and final mechanical energy are going to be composed of potential and kinetic energy. The way we define this problem by saying that this here is point 0, then that tells us that the skier's potential energy as they leave the ramp is 0. Height 0, therefore potential energy is 0. But they have a high amount of kinetic energy from the 14 meters a second. Sometime later, they're going to be at a peak of the arc traveling at 13 meters a second. So in the final situation, we'll still have both potential energy and kinetic energy. However, we can solve the problem because it's only referenced from the red line here. So let's see what we mean by this. Let me write this down and show you what I'm talking about. So the potential energy of the initial state plus the kinetic energy of the initial state is equal to the potential energy of the final situation plus kinetic energy of the final situation. So as I mentioned, the potential energy in this case goes to 0. And you're probably wondering, yes, they are some distance above the ground. The ground in this case would be the surface of the water. But we, for the question, set the reference point, because the question told us they only want the height reference to the top of the jump. So this here is 0. So here we're going to say that this line here, h equals 0. So if I take 0 and plug it into the potential energy formula, height 0, the rest of the terms, doesn't matter what they are, they all go to 0. So in this case, we lose the potential energy in the initial case. I don't need to worry about it. So the whole question is going to be defined by the kinetic energy of the initial state is equal to potential energy of the final state plus kinetic energy of the final state. Now, when you're working through this, you're probably seeing that we're just rewriting the same formula over and over again with an occasional step. But this is important because when you're doing this, you want to write all this down so that you can see where you crossed out to a 0, as I've done here in 2 cases, and what the resulting formula was. Because if you get to the end and you get a number that just doesn't make sense, or if you compare it against your friends and have a different number, or if you compare it against the answer key at the end and have a different number, if you've written down all your steps, it's going to make it a lot easier to find where your mistake was if you list each step that you did and the result from that step. If you just write this down and then skip here, and you wrote down potential energy initial instead of kinetic energy initial, you might miss that because you won't see what you did to get there. So make sure to write down all your steps, even though we're just rewriting the same thing over and over again. And along that line, let's now write or substitute in the formulas for potential and kinetic energy. Now, before I get too far into this one, let's take a look here. So again, just like in question number 1, the mass of the skier is not going to change. It's going to be the same mass in the beginning as it is in the end. So let's factor out the mass. Now, that's the same as we did last time, but here we've got this term plus this term. But just like if you were doing AB plus AC, you can factor the A out and do A times B plus C. And it doesn't matter how complex B or C are, you can always use this aspect. So here I can take the mass and factor it out all together and simplify my term to this. So when you're dealing with this, There's a lot of algebra and rearranging letters, but we need to do it in this fashion because we don't know what some of the distances are. We don't know what the height is from the water to the top of the ramp, and they don't tell us the mass of the skier. So we need to do it in this regard, or this method, in order to isolate the terms we don't know and find ways to eliminate them. So again, just like we did in the previous question, the mass is the same on both sides, so that cancels out. So now let's plug in the numbers that we know, and we can see what the height of this ramp would have to be for this situation to work out the way it is above. So the velocity of the skier in the first case is 14 meters per second, and that's going to be equal to 9.8 meters per second squared times the height in the final situation plus 1/2 times so let's go ahead and see if we can figure out what these numbers would be. So in the initial case, I've got 14 meters per second squared. So let's see what that is. So 14 meters per second squared gives us 196 times 0.5 is going to give us 98 meters squared per second squared. And that's going to be 9.8 because this part here has yet to change. And then we'll see what the next one is. So here, 13 squared is going to be 169 meters squared per second squared. Oh, and I see that I got a little, that shouldn't be there. And then multiply that by 1/2, and you're going to see that you get 84.5 . So now this has the same set of units, this has the same set of units, so we can use that in order to continue solving the problem. So we can take this, subtract it from both sides, and find out what it is. So let's do it that. Let's see what that would be. So 98 meters squared per second squared, subtract 84.5 meters squared per second squared is going to give us 13.5 meters squared per second squared. And then here's where we get into the point that we needed to make sure to keep our units the same. This is meters per second squared. That's meters squared per second squared. So just like we saw in the last video, once I do the division step here, we should have only meters remaining, which makes sense for a height. And we can find out what the height of this particular jump, or the height this skier would make if he went off the said jump. And let's call that 1.4. So here in this case, this is going to be 1.4 meters. So I want to take a moment and clarify this as well. It's useful to spend some time to work on doing the math of your units as well as the math on your numbers, such as I've done here, to make sure it works. Because if I went through and did this and I wound up with 1.4 seconds for my height, then that tells me I did something wrong and I don't want to check my work. My unit here is meters. I've got a height here, which makes sense. And so I can be rather confident this is the correct way to do the problem. It's a kind of a self-checking system. I know it takes a little more work, but it's a useful thing to do because when you're working on a real-world problem, or even if you're working on a test question, you won't have the answer key at hand, so you need ways to check and see if your numbers are making sense. So I hope that cleared up how to do question number 2.